Hi, welcome to the Putnam Museum. Today I'm talking about hyperbolic math, and I've basically made a few different shapes out of crochet and knitting, and we'll start with this one, which we'll pretend is a two-dimensional plane.
Okay.
And I'm going to give you the string, and I want you to see how many times you can go through this line and make it parallel to this line without intersecting this line.
Okay, so it has to go through the dot.
Yes.
Okay, so I can do it once.
Yep.
And I think that is it.
Yep, that's it. So Euclid's postulate basically examines the fact that on a two-dimensional plane, like a sheet of paper, you can go through this dot and be parallel to this line only one time.
Okay.
So you got that perfect. That's the first answer
All
to
right.
that one. The second one, then, we go into a sphere, and the sphere broke all the rules. It changed everything in Euclid's postulate, and I want you to see if you can make a parallel line on this.
Does it have to go through the dot again?
It has to go through the dot, it can't intersect this line, and it has to be parallel to this line.
Okay, so it has to be parallel and go through the dot.
Yeah, and that's normally what I would do too. I would normally make a parallel line like that. But on a sphere, a true line is actually cuts the sphere in half. So you have one half here and one half here, and that's called a true line. So it either has to be a longitudinal line like this, or a latitudinal line like the equator.
Okay,
because
so
it's cutting it in half.
do it.
So in other words, you got it. You can't make a parallel line because this isn't a true line. Otherwise, it would intersect the other line.
Okay.
So the answer is 0. All right, we got that one. Okay, and then I wanted to do the last plane, the hyperbolic plane, which is what we're talking about, hyperbolic math here. Here we have our similar line. Again, right here is our line, and this little green dot is our dot.
Okay.
And we're going to see if we can make a parallel line go through the dot and be parallel to this line right here.
To the red line. Okay, so it can go through once.
So,
Okay.
And if you follow the lines here, you'll see that you can take that line right there, and you can actually straighten it out, and it becomes parallel to that red line there. So we can do it once there, we can do it with the blue again, and then we can even do it with the green. So if you think we can do it 3 to 4 times, how many times do you think we can actually do it?
Infinite?
Yeah, you got it. So it's an infinite amount of times that you can make a parallel line.
Okay.
So I always bring this back to nature because people ask me at the Putnam, like, well, why do we care about this? Why do we care about parallel lines in hyperbolic math? And we care about it because in corals, which is actually right behind me, this is the Smithsonian Hyperbolic Coral Reef Project, and it was a great project to work on because it started out as just tubes and chicken wire, and we really assembled over 4,000 pieces of hand-crocheted coral to the coral reef. And so all of the shapes a lot of the shapes are made with hyperbolic math shapes. And in nature, if you look down at this coral right here, you can see that in nature, a lot of times corals will make these similar shapes because there's essentially more real estate. If you were a house or an animal that needed a house and you wanted more space to spread out, there's more space. And I'll show you what I'm talking about. So on the two-dimensional plane, if we were to take the circumference of a square, it would be a little bit more than the string, okay? If we were to take the circumference of the sphere, it's a little less than the string, so a little less. But if we were to take the circumference of a hyperbolic plane, you can see how much string it would actually take. It would take a lot more than what I have in my hand here. So you can see, as what I was talking about, real estate, animals love this shape because there's more space on the hyperbolic plane. So that's essentially why corals make this similar shape, and crocheters do too. So that's it.
That's interesting.
Yeah.
I like that.
Great. Well, thanks for coming in. We hope to see you at Putnam.